Okay, then the final thing I said was that there is this aspect of quaternions, which is that even though there are 3, 4 numbers, they lie on a 4D sphere. Just like if I told you that a particle always lies on a equation of a circle, then it'll always be on the boundary of the circle, right? This one here, x squared plus y squared equals 1. If it's on this surface, it's called it's a 4D sphere, very difficult to draw because you only have access to 3 dimensions. Then that's basically what you need to see. It turns out that in Euclidean space, which we've talked about, x, y, z, you can go from any point to another point, and there's no constraints. But when you go on a curve, you need to follow certain relations. This actually, geodesic is a path along a curve, and that path has to follow this relation. It has to ensure that the norm of q is 1. And it turns out that the approach we've used, the linear interpolation one, does not respect the geodesic path, and that's why you need to renormalize. Now, there's another way to do this. This is known as spherical linear interpolation, also known as SLERP. Okay, so usually you'll see this word LERP, L-E-R-P. That's the one I wrote down. It's a linear interpolation. But SLERP, what it does is, instead of having 1 minus t prime, it has this different factor for normalization. It basically follows sine 1 minus t prime theta, where theta can be found by computing the angle between qi, qf. That's just basically taking the dot product of qi, qf, you get theta, and then you can use that. So what this does is that it ensures that q slurp is always 1. So you're actually going on that 4D sphere. Your path is on the 4D sphere with the slurp. So you never have to normalize. Okay, so LERP is not equal to 1, but SLERP is equal to 1, which is why we want it. And then if you check the angular speed by using that formula, which I've written down here, you can check that the angular speed is actually constant using SLERP. So it not only helps you to go on the geodesic path, it also lets you keep the angular velocity constant. You can also calculate the acceleration, which is just taking the derivative of omega and omega b dot, and then that's the formula. You get simple chain rule gives you that formula. It's nothing new. The second part comes because you have q dot times q dot prime, I think, and then that gives you q dot square. So the other issue which we faced was that, I think I made a point here. So this leads to a non-constant angular velocity. What is that? It's basically the linear interpolation, LERP, gives this effect where the velocity, angular velocity, is not constant. Now, the good thing about LERP is that it is simple. Could we just use that instead of trying to use SLERP? So there's a way to do that, and it can be done by scaling. So we scale the time as follows. So this was linear scaling, such that this is basically both of these use this scaling. So t prime was t minus ti, tf minus ti. And then you can see it's 0 and 1 for the end time and start and end time. Okay, so what we'll do here is we'll choose a parameter s, which is a function of time, and we'll put whatever conditions we want on s. Think of that like the position. So that one, we want to ensure that the initial position is 0, final position is 1. Okay, this is just the time scaling. The second one is the initial, and so this is a mistake. This should be 1 dot, not 2 dots. Okay, this is saying that the initial velocity on s, final velocity on s is 0. Initial acceleration, final acceleration is 0. So there are 6 conditions. So we can assume a fifth order polynomial with 6 constants, solve for the 6 constants like we've done before, and this gives this simple rather straightforward expression because of the time scaling. You have something which is fifth order, but the terms second, first, and constant terms are 0. Now what we do is we modify both. We could do this with both LERP and SLERP. You just modify that time with s of t prime, sine, just modified with s of t.